derivatives and applications. True. What did you discuss in chapter 1? Pretty much towards the end of chapter 1, that's all we did. So this is if you want more applications of differentiation. We continue the same thing. Okay, so let's look at a few scenarios. I'm going to graph a few functions. So let's look at this function. And also let's look at this function. In a minute. Let's look at this one. Let's choose a few points on the graph of this function. A point here, a point here, a point here, a point here, one here, one here. At these points, I want to draw a tangent line at all points. I'm going to draw the tangent here. I'm going to draw the tangent here. I'm going to draw the tangent here. I'm going to draw the tangent here, and here, and here. Before we look at these tangents, would you agree that this function increases till something we call local max? So local is the same thing with relative. We use both interchangeably. You either say it's a local max or a relative max. Why local? Because I can show an interval around it. The function exists on both sides. And all the function values are smaller. This is the highest in that area, in that interval. Would you agree that then the function decreases to something we call a local or relative min? And then increases. Let's notice what happens at the local max and local min. What is the slope of the tangent at a local max? What is the slope of the tangent at a local min? What is the slope here? And what is the slope over there?
High.
0.
Thank you. So every peak, every max or min, local max, local min, will have a tangent that is always has a slope that is 0. There is also another possibility, to be exact. So what about this? I'll come back to this graph in a minute. What about here? What do we know about such a point? This is a function, it's continuous. But what do we know about this point? How do we call it? Anyone? How do we call this point? No one remembers? A cusp or a corner? So what did we say about this point? The function is continuous, but is it differentiable or not?
No.
Very good, awesome. Not differentiable. A function that is continuous is not always differentiable. If it has a cusp or a corner, it's not differentiable. So it's differentiable everywhere else, but not at the cusp. Okay? Now, on this example, let's choose few points. I'm going to draw the tangent. I'm going to draw the tangent. And I'll come back. Now, what happens? Can we draw a conclusion about the slope of these lines? Are they positive? These tangent lines, are they positive or negative? The slope of the positive. So here the slope is positive, also here, of the tangent. But what about here, when the function is decreasing? What is the slope of this line, of this tangent line?
Negative.
Negative. Stay with me. Let's look at this, and then we'll draw a conclusion, and then we'll come back to that. So can I say that the slope here is positive?
Yeah.
Can I say that here the slope is negative?
Yep.
Well, it happens that this is also a local max or relative max. The function is continuous there. It exists. It's not differentiable, but it has a local max. So here's our conclusion so far, also called first derivative test. And I like to present it with symbols. So let's say this is the first derivative. It's 0 or undefined, because it's undefined here. And if it changes sign from positive to negative, what type of point is this? Local, from positive to negative slope. Positive slope, negative slope. Positive slope for tangents, negative slope for tangents. What type of point will that be? Local,
Max.
local max. Stay with me. So let's look at the first derivative. And what if it's 0 at the point or undefined, but the sign changes like this, from negative to positive, from negative slope to positive slope. What type of point will that be?
Local min.
Local min. Excellent. So what happens now with this situation? Positive, positive, potentially 0, positive, positive, positive. So here the slope is 0. But the slope everywhere else of the tangent line is always positive. Is this, we also call it point of extrema. Is it a max or a min?
None.
No. And the reason is because the derivative does not change sign left and right of it. So let's also write that down. And then we'll jump to some examples in a minute. So if I have the first derivative, it could be 0 at a particular point or undefined, but it does not change sign. Oh, what type of point is this? Is it a max? Is it a min? No, no point of extrema. No point of max or min, called point of extrema or extremum, or no points of extrema if I use the plural. The same thing here. So if I have the first derivative 0 or undefined at the point, you'll see how this works in a minute. If I have this, same thing. If it doesn't change sign, where the derivative is 0, so we have to study the sign of the derivative. If the derivative is 0 or undefined and it does not change sign, no point of max min or no points of extrema. So let's look at a few applications to see what this means. So what are we trying to say here? We are trying to say that the derivative tells us a lot about the function. It tells us where the function has max min, and it also tells us when the function is increasing or decreasing. So let me write that down for you. F prime, number one, says if f of x is increasing or decreasing. That's number one. And number two, it gives, or just gives, I should say, gives max min of f of x. So two things we learned from the first derivative. We learn when the function is increasing or decreasing. And we also learn if the function has a max or a min. So let's look at a function and see how this works. So page 276. I'm going to share my screen. I don't think I have the book ready. I'm going to do this and do this and go here. And I'm going to jump to 3.2 so I can go back. That's what we learned from the first derivative about the function. If the function is increasing or decreasing, or if it has max min. Okay, so I want to start with talking about, so let me also talk about this before we choose a problem. So critical numbers. What is a critical number of a function? I just muted you, so unmute yourselves when you want to speak. So first of all, what is a critical number? A critical number of a function can come from two sources. A function doesn't have to have critical numbers at all. It doesn't have critical numbers. It doesn't have to have critical numbers coming from both. One or the other or none at all. No critical numbers. But if it has critical numbers, and we do have to look at both sources, those are from solving the equation f prime of x equals 0. Why? Because only when f prime of x is 0, the function may have max min. Not necessarily. But if the first derivative is 0, those points can be max min. Not necessarily. So that's one situation. I will have to solve f prime of x, the equation f prime of x equal to 0, to get these x values where the slope is 0. Number two, when f prime of x is undefined, and I put in parentheses, f of x is defined. Why? What's this? Haha, right here. F prime of x is undefined because it's a cusp or a corner, but the function is defined. So potentially that could be a local max or local min. That's why I explained, or I showed you these graphs, for you to understand that only if a function f prime equals 0 we get solutions, or and both of them can happen. F prime is undefined somewhere where the function is defined. If that's the case, then the function may have max min. And again, exactly what we just wrote here. When does the function have a max? If the first derivative is 0 or undefined, and it changes sign there, like here. Or even if the first derivative is 0 or undefined, but it doesn't change sign, there are no points of extrema. So bottom line, I'm going to write this down. If a function has no critical numbers, it cannot have max min. If it has critical numbers, there is no guarantee. We have to research and see what happens if the derivative changes sign. Okay, so let's write this down. This is important. Number one, if f of x has no critical numbers or number, there are no max min. Number two, if f of x has critical number or numbers, we must further investigate. If they are max min, the critical numbers. So if it has no critical numbers, there is nothing to investigate. It's guaranteed not to have max min. But if the function has critical number or numbers, we don't know if they turn into max min or not. We have to further investigate. And what are we going to investigate? The sign of the derivative left and right of that number. And then draw conclusions. Okay, so I'm going to share now. I want to go to okay, so here it is. For each function, find the critical numbers and any relative. They prefer relative, that's fine. Local or relative, they mean the same thing. Okay, so let's choose from 17 through 32, any problem, so we can investigate. Let's start with the polynomial first, and then we'll look at more sophisticated ones. So let me choose the first one. I'll choose 19. So this is g of x equals x to the third minus 12x and plus 5. So remember, we know that critical numbers come